The idea that everything is made of tiny particles is not new. This concept, known as atom theory, has revolutionized our understanding of the universe. It explains the fundamental nature of matter, revealing the building blocks from which everything we see and touch is constructed. Imagine a world where the air we breathe, the water we drink, and even our own bodies are all composed of minuscule particles, too small to be seen with the naked eye. The journey of atom theory is a testament to human curiosity and ingenuity. From the philosophical ponderings of ancient Greek philosophers to the sophisticated experiments of modern physics, our understanding of the atom has constantly evolved. The seeds of atom theory were sown in ancient Greece, where philosophers like Lysippus and Democritus first proposed the idea of indivisible particles. They called these particles atomos, meaning uncuttable or indivisible. These early thinkers believed that atoms were the fundamental, indestructible units of matter. Imagine trying to divide a piece of matter into smaller and smaller pieces. Democritus and his contemporaries reasoned that there must be a point where you reach a particle so small that it cannot be divided any further. This, they believed, was the essence of the atom. While lacking the tools for empirical investigation, these early philosophers relied on logic and observation. Their ideas, though revolutionary, were largely overshadowed by the prevailing theories of Aristotle. It wasn't until the 19th century that atom theory was resurrected and placed on a solid scientific footing. John Dalton, an English chemist and physicist, is credited with ushering in the era of modern atomic theory. In 1808, Dalton published his groundbreaking work, A New System of Chemical Philosophy, which outlined his atomic theory. Dalton's theory was rooted in experimental observations, particularly the law of conservation of mass and the law of definite proportions. These laws, established by Antoine Lavoisier and Joseph Proust, respectively, provided the empirical evidence needed to support the existence of atoms. Dalton's atomic theory proposed that all matter is made up of atoms, which are indivisible and indestructible particles. This concept explained why elements always react in fixed ratios, a cornerstone of modern chemistry. Dalton's work revolutionized the field of chemistry, providing a framework for understanding chemical reactions and the composition of matter. As scientists delved deeper into the atom, they began to uncover a world far more complex than Dalton could have imagined. Experiments in the late 19th and early 20th centuries revealed that the atom was not an indivisible entity, but rather a composite structure made up of even smaller particles. One of the most pivotal discoveries was the electron, a negatively charged particle found outside the atom's nucleus. J.J. Thomson, an English physicist, is credited with this groundbreaking discovery in 1897. His experiments with cathode rays demonstrated the existence of these tiny, negatively charged particles that were much smaller than atoms. Another crucial breakthrough came with the discovery of radioactivity by Henri Becquerel in 1896. These discoveries shattered the simplicity of Dalton's model, revealing the atom to be a dynamic entity with internal structure. The dawn of the 20th century witnessed a seismic shift in our understanding of the atom. Classical physics, with its deterministic laws, proved inadequate to explain the strange and counterintuitive behavior of the subatomic world. A new theory was needed, one that could embrace the inherent uncertainty and wave-particle duality observed at these minuscule scales. This revolution came in the form of quantum mechanics. Quantum mechanics, developed by physicists like Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, presented a radical departure from classical physics. It introduced the concept of quantization, where energy, momentum, and other physical quantities are not continuous but exist in discrete packets called quanta. The atom was no longer seen as a miniature solar system with electrons orbiting a central nucleus like planets around the sun. Instead, electrons were described by wave functions, mathematical expressions that represent the probability of finding an electron at a particular point in space. This new paradigm revolutionized our understanding of the atom and paved the way for countless technological advancements, including lasers, transistors, and modern electronics. In 1911, Ernest Rutherford, a New Zealand-born physicist, conducted his now famous gold foil experiment. This experiment, seemingly simple in its design, would revolutionize our understanding of the atom structure and pave the way for the development of nuclear physics. Rutherford's experiment involved bombarding a thin gold foil with alpha particles, positively charged particles emitted by radioactive materials, based on the prevailing plum pudding model of the atom, which envisioned electrons embedded in a diffuse positive charge. Rutherford expected the alpha particles to pass through the foil with minimal deflection. To his astonishment, a small fraction of the alpha particles were deflected at large angles, some even bouncing straight back. This unexpected result contradicted the plum pudding model and forced Rutherford to rethink the atom structure. Rutherford proposed that the atom's positive charge, instead of being evenly distributed, was concentrated in a tiny, dense central region, which he termed the nucleus. While Rutherford's model provided crucial insights into the atom structure, it still couldn't explain the stability of atoms or the discrete nature of atomic spectra. Niels Bohr, a Danish physicist, addressed these shortcomings with his revolutionary model of the atom, proposed in 1913. Bohr's model combined Rutherford's nuclear atom with the emerging concepts of quantization from quantum theory. He proposed that electrons, instead of orbiting the nucleus at any arbitrary distance, could only occupy specific quantized energy levels. These energy levels were analogous to rungs on a ladder, with electrons able to jump between levels but not exist in between. According to Bohr's model, when an electron absorbs energy, it jumps to a higher energy level. Conversely, when it falls back to a lower energy level, it emits energy in the form of light. Bohr's model successfully explained the discrete spectral lines observed in the light emitted by excited atoms. The development of quantum mechanics in the 1920s led to a more sophisticated and accurate model of the atom, known as the quantum mechanical model. This model, primarily developed by Erwin Schrödinger, abandoned the idea of electrons orbiting the nucleus in fixed paths and instead described them using wave functions. Wave functions are mathematical expressions that provide information about the probability of finding an electron in a particular region of space around the nucleus. Unlike Bohr's model, which assigned electrons to specific orbits, the quantum mechanical model describes electrons as existing in probability clouds, regions of space where there's a high likelihood of finding an electron. This model introduced the concept of orbitals, three-dimensional regions around the nucleus where electrons are most likely to be found. The quantum mechanical model successfully explained the behavior of atoms with multiple electrons and accurately predicted their spectral properties. It embraced the inherent uncertainty of the subatomic world, acknowledging that we can never know both the position and momentum of an electron with absolute certainty. Atom theory, far from being an abstract concept confined to textbooks, has had a profound impact on our lives, driving countless technological advancements that shape the modern world. From the harnessing of nuclear energy to the development of life-saving medical imaging techniques, our understanding of the atom has revolutionized various fields. One of the most impactful applications of atom theory is nuclear energy. By understanding the structure of atoms and the forces that bind the nucleus, scientists have been able to unlock the immense energy stored within atomic nuclei. This has led to the development of nuclear power plants, providing a significant source of electricity worldwide. However, it has also resulted in the creation of nuclear weapons, highlighting the ethical complexities associated with scientific advancements. Another area where atom theory has played a pivotal role is medical imaging. Techniques like X-rays, computed tomography, CT scans, and magnetic resonance imaging, MRI, rely on our understanding of how atoms interact with electromagnetic radiation. These technologies allow us to visualize the human body in unprecedented detail, enabling the diagnosis and treatment of various diseases. The story of atom theory is a testament to human curiosity and our relentless pursuit of understanding the universe around us. What began as a philosophical idea in ancient Greece has blossomed into one of the most successful and influential scientific theories of all time. Atom theory has not only revolutionized our understanding of matter, but has also provided the foundation for countless technological advancements that shape our daily lives. From the energy we use to the medical treatments we rely on, the impact of atom theory is ubiquitous. As we delve deeper into the realm of the very small, we continue to refine our understanding of the atom and its constituents. The discovery of subatomic particles like quarks and leptons, along with the development of the standard model of particle physics, has pushed the boundaries of our knowledge even further. The journey of atom theory is far from over. With each new discovery, we peel back another layer of the cosmic onion, revealing a universe of profound complexity and wonder.